Alrighty, let's see. Arithmetic sequences. Arithmetic sequences behave like linear functions. Okay, so we're going to tie today our arithmetic study of sequences with our previous things. Arithmetic sequences behave like linear functions in that we are adding, right? There's a common adder, and that's known as the slope or the rate of change of your linear, right? That's your m parts. And geometric sequences behave like exponential functions because they have a common multiplier, right? When we're adding things together, that's a linear sequence or an arithmetic sequence. And when you're multiplying things, that's a geometric sequence. Okay, so notice the similarities in their formulas. Okay, this is the one that we use most often, right? This one down here. The way that we talked about it in class, we used a k value of 1. We talked about the first term, so our formula was n minus 1, if you know your first term. But if you don't know your first term, then this top equation is really good to use. Okay, if you don't know a sub 1, then we can still figure out what the difference is using this formula. So that was one. We're actually going to use this later on in this video on our word problem on the back. Okay, so that's an important one to understand. If you don't know your first term, then you can use any two terms in your sequence. Your n and your k are any two terms in your sequence. Okay, now here's your geometric comparison. Right, so here we have g sub 0. This is the 0 term. We talked about it with an n value of 1. So we talked about g sub 1. If we know the first term, then your equation looked like this. And that's the one that we talked about most often. But once again, if you don't know your first term, then this is a formula that you're going to use to figure out what your ratio is. Okay, so we can use this one later to solve for your ratio if we don't know the first term of your sequence. Okay, and that will come up on our word problem later also. Okay, so notice your exponentials. The base of your exponential is the same as the ratio of your geometric sequence, right? Sometimes they're called the base in your exponential function, but it's called the ratio in your geometric sequence. Notice how they behave, right? So they're the same thing. A is your first term, and B is your ratio or your exponential growth factor. Okay? So then what if we compare the two of them? How do we know which is an exponential and which one is a linear? Well, notice in our linear function, there is an operation known as, right, plus. So these, the changes are constant. That's how we knew that things were a linear function, is your rate of changes were constants. And change is primarily based upon addition. Okay, and if it happened to be a minus, right, that's addition by a negative. So subtraction is really an addition problem also. So we have a constant rate of change, equal length input value intervals. Okay, so this is what we're going to look for first, is our equal length input value intervals. Is x changing constantly? Then what's happening with the y change? That's what we're looking for. Same thing over here. If x is changing at a constant rate, in this case, your outputs are happening proportionally. Right? Whenever we're multiplying, that's a proportionately, one of those two words. Anyway, there's a multiplying factor. The change is based on multiplication. Division is multiplication by a fraction. So even division is a multiplication problem, right? That's a times, a times b to the x, not a plus b to the x. Okay, so linear functions are adders and have a constant change. exponential functions are based upon multiplication and have a proportional change. So let's look at some of these in practice. So here we have a bunch of tables, right? We have x values and y values, and we want to know what type of a function best models these values. So the first thing we look for is our delta x. Are our x values have a constant interval change? Right? From 0 to 3, that's plus 3. 3 to 6 is plus 3. 6 to 9 is plus 3. 9 to 12 is plus 3. Okay, so yes, our input values, which are your x's, our inputs have a equally spaced interval, right? These are all 3 units apart. So now we're going to look at our x value, our y values, your outputs. Okay, how are these outputs changing? From 7 to 5 is minus 2. From 5 to 3 is minus 2. From 3 to 1 is minus 2. From 1 to minus 1 is minus 2. So for our x values that have the same interval, our y values have a constant rate of change. So what type of a function would this be? This would be a linear function. Okay? Because we have a constant rate of change. For our equal interval x values, the outputs are changing at a constant rate. Okay? Constant rate of change for output values. That's how we know this is linear. And we've looked at these linear ones before, right? So this should be nothing that's very new to you. Our change in y, our delta y over delta x is constant at negative 2/3. So this is a linear type of an equation. Okay, let's look at B. Check out your inputs. How are your inputs changing? Are they constant? Right? Plus 1, plus 1, plus 1, plus 1. Check. Our input values have a constant interval. So now let's check out your y values. Are they changing at a constant rate or not? So from 0 to 1 is plus 1, and then 1 to 4 is plus 3, 4 to 9 is plus 5, 9 to 16 is plus 7. Right? So that means this is not a linear function because the rate of change is not the same. But now let's examine these ones. What is our rate of change of our rates, right? Plus 2. 1 to 3 is plus 2. 3 to 5 is plus 2. 5 to 7 is plus 2. So what type of a function does this model? This model is a quadratic. Okay? Because our rates of our rate of change of our outputs is constant. Okay, so it's important to use the correct words when we're describing what's happening in our table. Okay, for a linear one, the rate of change of your outputs is constant. For your quadratic, the rate of the rate of changes, right? So how are your delta y's changing? That is making it a quadratic type of a model for your point values. Okay, but it all depends on your change in your x. If x is not a constant change, then these things do not happen. Okay, so in all of these tables, you'll notice that our rate of change for x is equal. 2, 2, 2, 2, 2. So we can look at the y's and make a good modular guess. So 1 to 2 is plus 1. 2 to 4 is plus 2. 4 to 8 is plus 4. 8 to 16 is plus 8. Well, that's not constant. So let's look at their rate of changes. 1 to 2 is plus 1. 2 to 4 is plus 2. 4 to 8 is plus 4. Notice what's happening with our numbers here. 1, 2, 4, 8, 16. 1, 2, 4, 8, probably 16. 1, 2, 4, probably 8, 16. right? So if we get this constant repetition of our numbers, of our values, that's a good indicator that we are talking about an exponential model here. So that means we're looking at multiplication. 1 to 2 is times 2. 2 to 4 is times 2. 4 to 8 is times 2. 8 to 16 is times 2. Okay, so this is how we know this is going to be an exponential. Okay, we have a proportional. For equal input values, our y values are proportional. In this case, it's a multiply by 2 or a times 2 factor. Right, which is what makes it exponential. Multiplication from term to term is a geometric sequence which correlates to an exponential growth type of a model. Okay, where your rate in this case is 2. Right, so this would be your rate of our function is multiplying by 2. And for our last example here, we have 5, 10, 15, 20, 25. So your x's have a constant change of plus 5 every time. And what are your y values doing from 80 to 40 to 20 to 10 to 5? Looks like it's divided by 2, divided by 2, divide by 2, divide by 2. Okay? Which is the same thing as multiplying by 1/2. So dividing by 2 and multiplying by 1/2 are mathematically the same. So this one would also be an exponential for the same reason. Exponential. Only in this case, this is a multiply by a factor of 1/2. Okay, multiply by 1/2, aka divided by 2. Okay, the outputs are proportional. Every output is half of the one before it. That is an exponential growth with a ratio of 1/2. So that would be our ratio for our exponential model if we were to write one. Okay, good. As long as your x's have a constant change, then we can decide on our y values. How are the y values changing? Okay, are we multiplying? Are we dividing? Is the rate of change constant, or is the rate itself constant for linears? Okay, let's get to our word problems. These are the fun ones. Okay, remember those formulas from before. We're told that there's a rumor that somebody won a contest. Oh, 3rd place in the contest. It says it can be modeled by a geometric sequence. So remember what our geometric sequences are. They have a common multiplier, right? Where 43 people heard the rumor on day 3. So as a number, that's our 3rd term. The 3rd term in our sequence is 43, right? So we have so many on day 1, so many on day 2. 43 people have heard the rumor on day 3. And 140 people have heard it on day 6. So somewhere down the line, there's day 5. Day 4, day 5. We don't know that. But on day 6, 140 people have heard the rumor. So that's G sub 6. So it says, the question is, how many people have heard the rumor on day 10? Right, so we're going to go down the line. This is day 7, 8, 9. I'm running out of space. 7, 8, 9. How many people have heard the rumor on day 10? That's our question. So in order to answer that question, I need to know my ratio. What is my ratio for my geometric sequence, right? We're told it's a geometric sequence. So we're not looking for a common difference, we're looking for a ratio. Okay, so we're going to use the formula with our n's and k's. G of n equals g sub k times r to the n minus k. This is the formula that we're going to use in order to solve this equation for R. We need to know what our ratio is going to be. Okay? So let's see, where do we put our things? So we're going to put G sub 6 right here. We're going to put G sub 6 right there. So that's 140. You always put your furthest down the line, I guess, your I don't know how to say it. Your 6th day in this case, because it's further along on your rumor mill, right? A longer date. That one goes first. Equals, we're going to put 43 here. Okay? So basically, this is going to be your G sub 6, and this is going to be G sub 3. That means our power is what? R to the 6 minus 3. Okay, according to our formula, we put the 6th term here, so our n value is 6. We put the 3rd term here, so your k value is 3. Okay, we put the 3rd term here, so this is your 6 minus 3, because those are the subscripts of these two terms. 140 equals 43r to the 6 minus 3. Okay, so now we're going to solve this equation for r. So first we divide by 43. Okay, we're going to need to have a calculator to do this eventually, so we're just going to leave this as 140 divided by 43 since those don't reduce. Equals r to the what power? R to the 3rd power. 6 minus 3 equals 3. Okay, so now we want to solve this equation for r, but how do we solve something if it's raised to the 3rd power? We take its 3rd roots, also known as the cube roots. Okay, so if we have a third of something raised to the 3rd power, we take its 3rd roots. So our root equals, when I put this into my calculator, the 3rd root of 140 divided by 43, I get 1.482 rounded to 3 decimal places. Okay, 1.482 is my ratio, right? That's my common multiplier. That's going to be the base of my exponent. So the question says, what is G sub 10? G sub 10. So that's what we're trying to figure out, G sub 10. So that's your variable, right? The 10th one. So now our n value is 10. So when I put 43 back in here, what was the k value of 43? Right, that was the 3rd day. So we're using that same formula over here. G sub n equals G sub k, r to the n minus k. Same formula, because you don't know our 1st term, so we're going to use our 3rd term. Okay, our ratio, well, we just calculated our ratio. That's 1.482. And what's our power going to be? 10 minus 3, right? 10 minus 3. So that's our subscript here. Your n value is 10. We're looking for the 10th day. And 43 was your 3rd day. Okay, you could have also used 140, but then our k would have been 6. Okay, you can use whichever one you want to use. When we type this into our calculator, we find out that 675 people, because we round to the nearest whole person, right? We round down. We can't have 0.2 of a person. That's not okay. So 675 people have heard the rumor after 10 days, right? After 10 days. So we're asked for the 10th day, so our answer includes that time right there. Okay? Good job. Remember these formulas. Okay? If you don't have them, write them down when you're doing these problems. Okay, now last example. Let's see, there's rows of seats in a theater that can be modeled by an arithmetic sequence. So this is telling us exactly what equation we should use, okay, which is good because we don't have to guess. Guessing is never good in a math class. It says the fifth row has 31 seats, so that's A sub 5. A because it's arithmetic. Our fifth row has 31 seats. Our 11th row has 49 seats. So A sub 11 equals 49. Determine how many seats there are in the 25th row. So we're looking for A sub 25. Right? We're assuming this is arithmetic, so we are adding seats to every single row. The question is, how many seats are we adding? We don't know what the common difference is. Right? In order to figure out what the 25th seat is, we have to know the difference. So we're going to go back to that formula that we had on the other page. A sub n equals A sub k plus d times n minus k. That's the formula that we're going to use. So, A sub n, that's going to be our 49. 49 is the term that we're looking for, 49. Our other term is 31. Okay, we don't know d, but do we know n and k? Yes, we do. 49 was our what term? That was the 11th term. Minus 31 was the 5th term. Okay? So whatever subscript is here, 49 is the 11th term. So n is 11. 31 is the 5th term. So k is 5. Okay, so we're going to do the math to solve this for d. So we calculate that our difference in between each of our terms is 3, right, when we solve this equation for d. Now that we know that, we can go back and figure out what our 25th seat is. So A sub 25 equals, you can either pick 31 or 49 for your A sub k. It doesn't matter which one of those two go here. Okay, I think I'm just going to leave it as 31 because that's the one I had before. So we'll put 31 back in there. Plus our difference, well, our difference was 3. We figured that out in the last part of the problem. And your n value, what's your n? Our n is 25 because that's the term that we're looking for. We're looking for the 25th term, so this is your n value minus 31. And what term was 31? 31 was the 5th term. Okay, so this is what we're going to do. We do this math to figure out what our 25th term is. And our final answer is 91 seats. Okay, so if you don't know the first term, you use this general formula in order to figure out what your variable, your ratio, or your common difference is. Okay, those are the hardest types of these type of problems, so I'm glad we got to do some.